Again, sorry. Okay. Without further more ado, okay, let me continue with the presentation. Okay, I hope you guys are having a good day because apparently I'm not, and also mobile phones are also not having a good day because yesterday researchers found 32 zero-day vulnerabilities in different smartphones, and they actually exploited them to get almost 5K as prize money. This happened like yesterday night at 2 a.m. Okay. And yeah, in this presentation, we'll show how we found 36 bugs in 7 different devices. And these bugs could be cached out. I mean, if you can make an exploit, like Google offers good bug bounty for this. And we'll show techniques how we are able to find these 36 bugs. Okay, first a little primer on kernel drivers. Kernel drivers provide an interface to interact with hardware. These are usually written by hardware vendors because they need to know how to interact with the hardware. And they run in kernel space because they need unlimited access to all the system resources. Linux kernel drivers, they expose, the interface for the drivers in Linux kernel is exposed by a file in in /dev directory mostly. An example is the /dev/qccom. It's a device driver for QC interface, which is exposed on most of the Qualcomm phones. The way to interact with the device drivers on Linux is read, write, and ioctls. Read, write, as you might be aware, these are just the system calls you use to interact with the files. And ioctl is a special kind of a system call that I will be describing later why ioctl is special and why it can be really buggy. And these drivers run in kernel space, and Linux kernel being monolithic, any bug that you find in the driver can be exploited to get arbitrary kernel code execution. Now, moreover, these drivers are tightly coupled with the device, and the drivers are actually very self-contained with respect to the source code structure. If you refer the driver source code directory in the Linux kernel, you can easily identify all the source code files that belong to a driver. And these drivers allow for easy customization of the Linux kernel, which is kind of evident from all the Android devices and IoT devices that you see around which use Linux kernel as their base. Now let's look at Android kernel. Android kernel is based on Linux kernel, and it dominates smartphone OS market with 86.8%. And it has a lot of vendors, almost 100 vendors, close to 100 vendors, and it has a lot of hardware, which needs a lot of drivers. And yes, as evident from yesterday and also from all the Android security bulletins from past couple of years, Android kernel bugs are increasing. And most of these bugs are actually from the vendor drivers. This was shown by Jeff Vendor from Google team in last year in Linux Foundation Summit. Where are these bugs in the drivers, right? We have 85% bugs. What are the buggy components of the driver? Looks like buggy components of the drivers are actually ioctls. And I'll show later like why these ioctls are complex and why these ioctls could be buggy. Okay, let's look at what is this ioctl which is so buggy. Ioctl stands for input-output control. This is a system call specified by the BSD, and it allows to implement some operations which cannot be modeled easily using read and write system calls. And similar to read and write system calls, IO control system call or ioctl is bound to a file. So it requires a valid file descriptor for the system call to succeed. This slide shows a actually a simplified signature of ioctl system call, where the first argument is the file descriptor. It has to be a valid file descriptor. And second two arguments are unverified user data, where there is no verification done by the Linux kernel for these two values. The slide shows an actual real-world example of a ioctl system call implemented by the camera ISP driver in MediaTek devices. Here, these are the two parameters completely controlled by user. Now you can see that the ioctl first checks the value of command against ISP read register, a constant value. If the check passes, it expects the param to be a pointer to a user space memory, which actually points to a structure of ISP register IO struct. And copy from user is a method which copies the memory content from user space to the kernel space. Similarly, if the command value is write register, it expects the param to be a pointer to a structure of different types, so on and so forth. Now, how can we find vulnerabilities in ioctls? Okay, let's consult our classic friend static analysis. But it could lead to a lot of false positives. Moreover, static analysis, it's very hard to find uh, common bug classes like use after free, which is one of the bug used in yesterday's exploit chain, because use after free requires us to understand pointer interactions, and our old friend alias analysis bites back, and it will end up being a lot of false positives. The other technique is dynamic analysis, specifically fuzzing. It's easy, and the fuzzing gives us a crash input, which makes it easy to trash the bugs, and it can find actually complex bugs. Specifically in Diffuse, we used Diffuse while fuzzing on Huawei. We found a design flaw by using which we were able to change the serial number from user space of Android, which by design no one should be able to do. Okay, let's fuzz. Okay. We can simply generate random input data to a driver and hope kernel panics. However, this will not work because ioctls, as I shown in the previous slides, have highly structured input. So here, the command value has to satisfy the constraint that it has to be ISP re-registers, or else it will always go, like it will never reach the switch, and it will always just exit. So only then the param value will be used. So this is in plain language, what's the constraint? Similar, okay, so one can easily say that, okay, since the constraint is only on command, and the toughest constraint is a param because it has to be a pointer, let's make a param pointing to some arbitrary user space memory, but make it a valid pointer. However, that will not work because structures could be complex. This can contain pointers within themselves, so you need to handle those accordingly. You cannot just make param point to arbitrary user space memory and hope the driver works, or hope the fuzzing works. Moreover, the command, depending on the value of command, the param has to point to different structure types. Like if the command is write register, it should point to reg.io, which is actually same as the read register. However, if the command is hold reg time, the pointer has to point to ISP hold time enum type. This actually is a simplified example of the bug we actually found using Diffuse. Here, the bug is arbitrary kernel heap write here because the value of foo is completely controlled by user as shown, because you copy param into foo and foo.idx is used as an index without having any checks. Okay, what's the problem here? The problem is, of course, arbitrary kernel heap write, but the thing is, the input that it expects is highly constrained. Number one is command value has to be equal to 1337, and the param should be a valid user pointer, and it should point to a structure where the first field should be equal to 77, and the second field should be greater than 128. Then only you can actually have a crash or an exploit for this. So Diffuse tries to solve this. The way Diffuse tries to solve this is to recover all the command types, command values, and the parameter types in an automated way, in the hope that this will help reduce the state space of fuzzing and helps fuzzer to reach the buggy code parts easily. This is the overall flow of Diffuse, where the first component is the interface recovery, which uses static analysis to recover the command types, command values and parameter types. And the second component is structure generation, which generates the binary data corresponding to the structures. And the third component is on-device execution, which actually executes this random data by making the ioctl system call. Let's look at the first component of interface recovery, build system instrumentation. Here, the target is to create a consolidated bitcode file for the entire driver. So to do this, we instrument the build system, we compile the kernel using GCC, we capture all the compilation commands, we convert each compilation commands into corresponding Clang version by replacing compiler flags accordingly, and then we link the related bitcode files into a consolidated bitcode files. I simplified it a lot, but it's a really tedious process. There is a lot of engineering effort involved. This actually enables all the static analysis to be done on Linux kernel drivers. There was a recent paper called Driver Checker, which was enabled because of this instrumentation. So this is a nice thing. This is a nice engineering effort, and you can use it to do many different static analysis or even dynamic analysis on Linux kernel drivers. And the second is ioctl handler identification. So here we need to identify the function in the driver which handles the ioctl system call. So the way we identify is there is a standard mechanism where each driver uses to register an ioctl function. So it is based on defining a file operation structure and assigning the function to the ioctl field of the structure, specifically unlocked ioctl. The function that is assigned to the field is the function which will be called when ioctl system call is made on that particular device file. So, and this step is actually extremely dependent on the device types. You can refer the paper for more details. The second is device file detection. This step deals with identifying the actual device path on the phone to which we need to interact to talk with the driver. So here we use several heuristics based on the driver type, and by linking the file operation structure, which was used to register ioctl function, and the device type, we are able to identify the device file name that is used. However, this technique will not work for dynamically generated names. For example, this one here, the device name is actually dynamically generated, and it's impossible to compute the device name statically. So device file name detection actually fails in these cases. Next is the command value determination and argument type identification. Here, what we do is we do a path-sensitive interprocedural analysis where we start from the entry of ioctl function and we traverse all the paths that can lead to the copy from user function call. And along all the paths, we collect the constraints on the command value. And at the end, when we reach copy from user, we compute all the possible types for the destination argument. So this gives us possible values that the command needs to have along that path and the possible types the ioctl function is expecting the parameter to be. So if we combine these two, this should give us the over approximation of all the possible commands of all the possible types. So we just do a combinatorial thing and we emit these as the possible command values and possible types of the params. So to give an example, this is the ISP ioctl. Here the command value is checked against this. So we traverse this basic block and we collect the constraint on command, which is ISP buff control. Since this is interprocedural, we follow the method. Here ISP buff control function is expecting a param. We track the param. And then when we reach the copy from user, we need to identify the destination parameter, which is RT buff control. We need to identify that type. We use simple static analysis to identify it. Although this is not easy in all cases because you could have void star, you could have typecasting. We handle that. We actually compute, we do a simple type inference to compute all the possible types that the destination parameter can have. So that we can have an over approximation of possible types of the destination parameter. Note that it's not easy to determine from the size. It is not easy to determine the value, although you could have some heuristics, but that's very unsound heuristics. Okay. Now finding the structure definition. So the previous step just identified the name of the structure. Now we need to identify the structure definition, which gives us the layout of the structure, from which we can generate the fuzzy data to be the random data that we can use to fuzz. So to do this, we reuse the compiler instrumentation, and using that we generate the preprocessed files, and we use C2XML to convert the corresponding structures into an XML format from which you can easily generate the random data that you want. However, there are some engineering issues that you need to take care because of padding. C structures could be padded, so you need to handle padding there and generate the structures accordingly. So at the end, let me summarize what interface recovery does. So given the kernel source code, it automatically generates the consolidated bitcode file for each driver. It identifies the device file names. It identifies the commands and types expected for the param argument. And all these three things combined, they form the interface for the driver. Now, see structure generation. Given the interface of a driver, structure generation, given this structure, we need to generate random data for this structure. So let's look at the fields. The first field is an enum, where the possible values are, like, there are 9 possible values, although you could fuzz it with random value, but it'll be good if one of these values belongs to this enum because it helps going into the code much deeper. Similarly, buff here, DMA enum, buff ID is type of DMA enum, which again has 22 possible values. An interesting thing is here data pointer. Data pointer now is a pointer to a different structure. The structure is shown below. However, this structure again contains some other structures. And those structures could again contain pointers. So you could have a recursive list of pointers and pointers pointing to each other. So structure generation actually handles them and resolves the recursion by just traversing with like one depth below, and it generates a set of blobs and corresponding places where the pointer should be fixed, and it's called mapping. We call it mapping. So it generates a set of blobs and a mapping information using which the on-device component can generate the data. Okay, yeah. On-device component actually gets the data from the structure generation. It gets the blobs and the mapping. It maps the binary data and do pointer fix up, and it opens the device and does the actual ioctl system call. If the device crashes, it captures the input that resulted the crash and gives the input back for the triage. To evaluate, we evaluated Diffuse on 7 different devices across 5 different manufacturers and 4 different chipsets. So device name recovery, device name recovery was not that effective because of the dynamic names, as I mentioned before. Out of 789 ioctl handlers, we were able to identify device names for only 469, which is 60% effectiveness. 40% of them we missed mostly because of dynamic names. And moreover, an interesting thing is most of these dynamic names come from mainline kernel, so which we think that it can be easily circumvented if we have like manual effort of one time for a Linux kernel, which can be applied to any Linux kernel because the mainline kernel driver doesn't change much. So for typeless command ID, we were able to recover various types and commands. And 53% of these commands actually expect a pointer, expect the param to be a pointer to a structure type. So this shows that if we don't have the structure recovery, we'll not be able to fuzz this 53% of the commands effectively. And we have 90% accuracy. We computed this by random sampling. Since there were various commands and param types, we randomly sampled 5 ioctls from each of the device, resulting in 35 ioctls, and we verified the command value and the param is the actual thing from manually looking at the source code. We got 10% false positives. Note that we never miss any type, although we may over-approximate some type to be required for some command because of the combinatorial thing that we do. To evaluate fuzzing, we have 5 different variations of our fuzzer, where the first is the base syscaller. Syscaller is the state-of-the-art Linux kernel system call fuzzer. We just use the base system call fuzzer to evaluate. Next, we progressively add more interface information to the syscaller. In the second variation, we add device path to the syscaller. In the third variation, we add command IDs to the syscaller. And the third variation, we add entire interface information to the syscaller. And at the end, where we just want to understand how effective is the interface information, we just use standalone fuzzer, which is very dumb fuzzer with just interface information, to see that do we actually need smart fuzzing or interface information may be enough to fuzz the drivers. This table shows the results. So we found 36 unique bugs across 7 different phones. And as you can see, the more interface information we provide to the syscaller, the more bugs it finds. So if you just add path, it could find only 3. If you give it commands, it can find 22 bugs. When we gave the entire interface information, it was able to find 34 bugs. And an interesting thing to note here is our fuzzer, which is Diffuse M, which just uses interface information without the complex features of syscaller. It was able to find 30 bugs, which is not bad for a fuzzer which was written in like 100 lines of Python. because it shows that how relevant the interface information is for the driver fuzzing. And to give a summary of the bug types that we found, like there are bugs which are arbitrary read, arbitrary write, and buffer overflows, which can be used to get arbitrary kernel code execution. An interesting thing is there are 6 assert failures. Although assert failures are usually considered moderate or ignored mostly, we were able to exploit one of this assert failure to get kernel write. It's an interesting thing. We may actually release a blog on that, but yeah, assert failures cannot be taken lightly. Okay, to conclude, we provided a method to extract interface information from the driver source code. We show that interface information can be used to effectively fuzz Linux kernel drivers, and we open source all our source code at this particular GitHub link. That's it. Thank you.
Hi, I'm Billy from Android Security. Thank you for your work. I really enjoy it. For several questions. The first one is, have you considered using your method to extract device information and then to translate that into syscaller descriptors?
Yes,
versus like just, you know.
That's an extremely interesting question. Thank you for asking. Actually, the way we do it, the interface information actually is emitted as an XML file, which, as you can see, can be easily translated into the syscall Go structures, as you know. Yeah.
Okay, so that's possible. And
yes, we have a script actually which can do that.
Cool. Yeah, thanks.
Thank you. That's exactly, yeah, that's a good question. Yes, so there are some commands which actually set some global parameter, and the other ioctl command actually retrieves those global parameters. We were able to trigger some of those bugs, but we don't model that in the current diffuse version. But we definitely can model, like we can group certain ioctl commands based on the global values that they touch, so that you can effectively fuzz that group to identify more deeper bugs. Thank you. So anywhere where there is a relation between parameters of a command, we can use our system, we can extend our system to define, like to extract the interface. But we tested only on Linux kernel drivers. So we could actually extend that to like any interface which expects some constraints between different values of the parameters. Although we don't use constraint solver, so if the constraints are complex, we may not be able to recover all the commands. But if we use constraint solver along with our method, I think we should be able to do that for any interface in general.